In this lecture, we're going to study another method, the implicit Euler method, to find solution for initial value problems. Similar to the explicit Euler method, we're going to derive the implicit Euler method by first considering the initial value problem given by dx by dt, which is the rate of change of x with respect to t, given as a function of x and t. We're going to use a Taylor expansion. When we developed the explicit Euler, we used the Taylor expansion around the point xi. Here we're going to use an Euler expansion, a Taylor expansion around the point x at time equal to ti plus 1. In this case, you can write xi, which is the value of x at the time point ti. It's equal to the value of x at time point ti plus 1 minus the first derivative evaluated at ti plus 1 multiplied by delta t. And here we're using minus. This negative sign appears because h is actually written as ti plus 1 minus ti, so that we can always use a positive number here. This is the Taylor expansion. If we only use those two terms, then we know that the error term is directly proportional to h squared. We know that dx by dt is equal to the value of this function f evaluated at the point xi plus 1 and the time point t sub I plus 1. If we ignore the error term, we can assume that the value of x at time point ti plus 1 is approximately equal to this xi plus 1, which is equal to x sub I plus the rate multiplied by h. Really, the difference between the implicit Euler and the explicit Euler is that in the explicit Euler in the previous lecture, this f was evaluated at x sub I and t sub I. Here f is evaluated at x sub I plus 1 and t sub I plus 1. Similar to the explicit Euler method, the implicit Euler method has a local error for every time step that's directly proportional to h squared. The total error, when I consider an interval of length L, that's divided into n subintervals, n is equal to L divided by the width of one subinterval, then the total error will be equal to this number n multiplied by the local error, which will make the error directly proportional to h. So both the explicit Euler and the implicit Euler both have the same order of error. So let's look at this visually. So the function x is the function that I'm trying to approximate. It's an initial value problem, which means I know let's say I know at the time t sub I know the value of xi, and I want to advance in time and find the value of xi plus 1. So using this, xi plus 1 is equal to xi plus the rate multiplied by h. The explicit Euler method, the previous one, we evaluated the rate at that particular point. Here, we're evaluating the rate at the next point, which in some situations might be a little bit problematic or requires can cause the equations to become nonlinear if I don't know the value, because I don't really know the value of xi plus 1 and I'm trying to calculate the value of the rate at that new point. So what we're saying is that at ti plus 1 there is a rate, which is the slope of the curve. I'm going to use that slope of the curve to advance from xi. So knowing the slope at ti plus 1, So this is the slope, which is given as a function of xi plus 1 and ti plus 1. I know the slope here, and then I can advance from this point along this slope by distance, when I move horizontally by distance h, to reach the value of xi plus 1, which is an approximation for the true value which lies on the curve. And this shows the expected error, the local error in one time increment. As I mentioned, the equations can become nonlinear if f is nonlinear function of x sub I plus 1, and we're going to show this in an example at the end of the lecture today. So let's go through some examples. We're first going to solve the same examples that we solved in the explicit Euler method. So I would ask you to, if you haven't done so, please watch the explicit Euler method lecture first, and then watch this lecture. So here we're going to solve the same example. We're trying to predict the population, the Canadian population, knowing that the birth rate and the death rate. And so when we also have two different cases, one with a small birth rate at 2.5% and another one with a birth rate of 6%. So in the first case, the rate of change, or the rate of increase in the population, is equal to 15%, or sorry, 1.5%. So it's 0.015 multiplied by x. The implicit Euler states the new, if you use a time step, let's say 1 year, so we're going to use a time step of 1 year, the population at time ti plus 1 is equal to the population at time t sub I, plus the time step h, which is the difference in time between the two time points. In here we're going to take it as 1, multiplied by the rate. The rate is evaluated at the new point at xi plus 1, and t is equal to ti plus 1. So this is the rate. So xi plus 1 is equal to xi plus h multiplied by this value, evaluated at the new point at xi sub I plus 1. And so notice here, xi plus 1 is unknown. It's the unknown that I'm trying to find, which means I have to rearrange the equations to be able to find xi plus 1. So rearranging the equations and noticing that h is equal to 1 will give me this formula: x sub I plus 1 is equal to x sub I divided by 1 minus 0.015. Okay, that's easy. If I know the first xi, I can find the new x sub I plus 1 and advance in time to find all the possible all the populations as we advance in time up to 50 years. So we can do this. So initially we have x0 is 35, x1 is 35 divided by 1 minus 0.015 will give me 35.533, which means that the population after 1 year should be 35.533 million. After 2 years, the population will be 35.533 divided by 1 minus 0.015, 36.074 million, and so on. So as I advance in time, the population increases, and after 50 years, the population is predicted using the implicit Euler method as 74.517 million. We already know the true value because the equation can be integrated. We can find a closed form solution for the integral, and so the error is equal to the true value minus the numerical value obtained using the explicit Euler method, which is 74.517, will give me negative 0.4 million, which is, as I mentioned, it's a very small number similar to the explicit Euler method, and that small number, this is a very small number because the rate is actually very small. The relative error is actually equal to negative 0.5%. Here you can see the blue dots represent the solution using the implicit Euler method. The black dot shows the solution using the explicit Euler method, and in between them there's a line that gives the true value of the population given the closed form solution. You can see when the rate is small, the values are actually very close to each other. When the rate is high, k is equal to the rate of birth was 6% minus the death rate, so which was 1%, gives me 5%. So the rate of increase is actually 5%, 0.05. You can see the black dot gives me, it uses the explicit Euler. The blue dots are the implicit Euler. They're both relatively accurate for this particular example, but of course the error increases as we march in time. You might want to think, for this example, it's not always general, but maybe look at the curve and try to understand why would the implicit Euler method overpredict the population. So you can see the blue is over-predicting the population, while the explicit Euler method, which is the black dots, why are they under-predicting the population? So think about it and maybe try to figure it out. And just remember, this is not a general rule. This just applies to this particular example. Of course, changing the changing the time, the time increment will making it bigger will lead to a solution that's not as accurate. As you can see here on the left, when h is very small, the black dots are very close to the true value predicted by the blue line. When we increase h, you can see that the black dots start deviating from the true value, and you can log on the website and play around with the tool and see what happens when h changes. We're going to solve the second example that we also presented in the explicit Euler method. In this example, we have we're discussing the change in the concentration of a pollutant in a given lake whose volume is constant. And you can visit the last lecture to see how we derived this differential equation. dc by dt, the rate of change of the concentration, is given by this equation, which is function of time. So t appears, and the concentration itself appears as well. So the rate is function of the concentration and of t. So using the implicit Euler method, given if we assume that the time increment h is equal to 1, we can find the ci plus 1 or c sub I plus 1 as equal to ci plus h multiplied by the rate. The rate for the implicit Euler method is calculated at the time point t sub I plus 1 and c sub I plus 1. As I mentioned, we don't know ci plus 1, this is the unknown. And of course we know the value of ti plus 1 is equal to ti plus the time increment, which is h, which is 1 in this case. So we know ti plus 1, but we don't know ci plus 1. We don't know ci plus 1, so we need to rearrange the equation to put ci plus 1 on one side. And then we get this equation that is a function of ci and t sub I plus 1. Using the initial conditions, we know that when the time was 0, the concentration was given as 5 parts per billion. Knowing that, we can advance in time and see how the concentration changes every, I think each here is per day, so every day, how the concentration changes every day. So when the time was 0, the concentration was 5. When we substitute, we'll get that C1 is equal to 4.9999, and so on. If we advance in time, and you can do this in Excel or you can do this in Mathematica, you can create this curve that is exactly similar to the curve that we obtained when we did the explicit Euler method. The next example discusses the stability of this method. If you remember the explicit Euler method, when we presented it, there was an example where we showed exactly this example, we showed that if h is chosen too large, then the solution will oscillate wildly, and it will not really give any useful information. This only applies to the explicit Euler method. The implicit Euler method does not show this behavior, and we're not going to go into the theoretical basis for that, but we're just going to show this with the same example. Dx by dt, the rate is equal to -1 multiplied by x, and we have an initial condition when time is 0, x0 is equal to 1, and we're going to compare using step size of h.1 and the step size of h equal 3. The implicit Euler scheme, x sub I plus 1 is equal to xi plus h multiplied by the rate. But which rate? Don't forget, this is the implicit Euler scheme evaluated at x sub I plus 1. Alright, dx by dt is given as equal to -x, so I'm going to substitute -x at sub I plus 1. Then, rearranging, I need to rearrange to bring xi plus 1 into one side, because this is the variable that I'm trying to find, the value that I'm trying to find. So xi plus 1 is equal to xi divided 1 plus h. Remember, we can also think that xi is equal to the 1 before it divided by 1 plus h. Therefore, xi plus 1 will be equal to x0 divided by 1 plus h power I plus 1. H is a positive number. The term 1 over 1 plus h power I plus 1 is always bounded, because this is a number higher than 1 and it appears in the denominator and to a power of a positive a positive number. So this is always bounded, and so xi plus 1 is always bounded. And you can see here what happens when I change h. For a small value of h, I get a very nice and accurate solution. A higher value of h times step, the solution is not very accurate, but it's still stable. It does not show the wild oscillations that appeared in the previous lecture when we solved this example using the explicit Euler method. Alright, the last example, we are going to show the one small disadvantage for this method. So the advantage of this method is that it is stable. It's actually conditionally stable. It's always stable, unlike the explicit Euler method, which is not always stable. The implicit Euler method is always stable. I think the term, the exact term is that it's unconditionally stable. But the problem with it is that because we're calculating the slope at the point that we're trying to find, we're calculating the slope in the future, the equations can become nonlinear, and we will have to invoke the Newton-Raphson method to be able to solve it. So let's look at this example that shows this case. The slope is given by this nonlinear equation of x. dx by dt is equal to 3x squared plus 2x. We have an initial value. When the time is 0, x is equal to a -5, and I'd like to advance in time. Time goes from 0 to 5. I'd like to know what the value of x is as time goes from 0 to 5 using a time step of 0.1. Luckily, I have an exact solution. I can actually integrate this equation to find a value of x. X is given by this formula. So if I employ the implicit Euler method, I will assume xi plus 1 is equal to xi plus a value of h multiplied by the slope. The slope is evaluated at the new time point. Alright, so xi plus 1 is equal to xi plus h. H here is the time increment, is given as 0.1 multiplied by these values. The unknown, don't forget that the unknown is xi plus 1. So this becomes a nonlinear equation in xi plus 1. And the only way I can solve it is using the Newton-Raphson method. For example, the initial value of x0 is -5, h is equal to 0.1. The initial time point is 0, the new time point is 0.1. So x1 is equal to, when I substitute, xi is -5, h is 0.1, ti plus 1 is 0.1, x1 squared is the unknown, plus 2x1. So this is a nonlinear equation in x1. I can employ the Newton-Raphson method, I can program it myself, or I'm here using the find root within Mathematica, find root to find the solution to this equation. And I can find that x1, which is the value of x when the time is equal to 0.1, is given by -5.82576. Advancing in time, I'm going to try to find the value of x2 at t2. t2 is equal to 0.2. x2, again, using this equation, the new x is equal to the older x plus h multiplied by the new time, x, the new x squared plus 2, the new x, will give me this equation. x2 is equal to x1. Sorry, x2 is equal to x1 plus h, which is 0.1, plus the slope given by this term, 0.2 x2 squared plus 2x2. Again, to solve this, I need to employ the Newton-Raphson method to give me, which will give me this value. As we advance in time, we're going to get that blue curve. The blue curve is the true value given by this equation, and the dots are the numerical solution obtained using the implicit Euler method. Here in the red square, I'm asking what is the difference about example 4 using the implicit Euler method versus the first 3 examples. Don't forget that we had to employ the Newton-Raphson method here to be able to solve for the different time points because of the nonlinearity of the equation, and because I'm using the slopes at the time point that I have not. I'm using the slopes at the point that I have not found yet. Here you have a code that solves the implicit that gives you a table of the time and the value of x using the implicit Euler method given a rate. The difference, if you compare this code with the code from the explicit Euler method, the biggest difference is here we're using find root to be able to solve for x. So you should study this code and try to understand how it is employing the implicit Euler method to solve the initial value problems.